Hey folks, we're going to look at the next section in our book now. It is on rate of change, which some of you may have known as slope. What I'd like you to do is make sure you have this sheet. I have yellow copies, but if not, a link to this actual page is on my homework site, so you can feel free to print one out and take notes on it. It has all of our examples we're going to be using today, so you want to make sure that you really do have it handy and that you're taking your notes on this sheet. Now, before I start talking about slope and rate of change, what I want you to do before I kind of get into it, I want you to put down things that you already know. We've talked about slope a little bit in class when it comes to graphing lines, so put what you know here. You know there's a ratio. Maybe you've heard other things about it or you know other things. So take a second, write some things down, and then we'll discuss them in a moment. All right, now that you've put down some things of your own for what you think slope is, let's add to your list. Okay, we know that slope is a fraction, and I'm sure most of you thought of it as rise over run. Well, this is true. Slope is rise over run. It's our change in how we go up or down, and our run, how we go side to side. And we can use that pattern to graph lines. Okay? We might even know slope-intercept form. That sometimes it's called M. That's our slope when we're looking at y equals mx plus b. Okay? And we've been graphing lines using that. But there's more to slope than what we've already been talking about. Okay? But generally speaking, you need to know that it can be shown as a fraction. It's a ratio of rise over run. We can use it to graph lines. We can also use it to interpret what things mean, okay? By calling it the rate of change, or how our lines change, how our data changes. So all of these are things that hopefully are somewhat familiar. We're going to add to this list today. Okay, we're going to look at how we can calculate slope, and we're going to look at how we can recognize slope in a bunch of different instances. We're going to look at tables, we're going to look at graphs, and then we're going to look at a set of 2 points, or 2 solutions, okay, to whatever that linear equation is. So on this sheet, let's scooch right down to our next section about tables. All right, let's look at how we can find slope or rate of change. They're synonymous, they mean the same thing, in tables, okay? We're going to use the table right here to find the rate of change and explain what it means. Now, being able to find it and explain what it means is one of our standards, okay? Slope, doing this exact thing we're going to do a few times today, is exactly what you need to be doing in order to meet that standard. So when we look at rate of change, okay, which I told you is kind of the same thing as slope, it's just synonymous, they mean the same thing. We're looking at the change in y, which is our rise, over the change in x, which is our run. If you think about it, our graph, okay, our y-axis, that dictates whether we're going up or down, okay? So our change in y is also known as our rise, and then our change in x, our x-axis is horizontal, it brings us side to side, is going to be our run, okay? So keeping that in mind, if we want to find the change of something, we're going to be finding the difference. So for example, I'm going to pick 2 items on my table. I'll choose the first one right here, 278, and the last one, 6,234. Okay? I already know these are the x's, that's the number of computer games, and then our total cost is our y variable, our dependent variable, on how much it's going to cost us per game. And not really per game, but for that total amount. So now to do our slope, our rate of change, we're going to do our change in y. So how much the change was between these 2 y values. And I find the change in these by finding the difference, which is subtraction. So what I'm going to do is I'm going to take 234, and I'm going to subtract from it my other y value, 78. And I'm going to put that over my change in x. I have to use the same points. So I'm going to go here, because I started with 234. I'm going to start with the corresponding x value, 6. And to find how much it changed, I'm going to find the difference between it and 2. So 6 minus 2. So 234 minus 78. I have to write it to the side. I borrow. That's going to be 6. Borrow again. That's going to be 5. 156. Over 6 minus 2 is 4. Okay? Now at this point I have a couple options. I could keep this rate of change as a fraction of rise over run. And I can even explain what this means. Okay? So 156 goes with my y. My y is my cost. So this isn't just 156. This is $156. Now the 4 goes with my x's, right? Rise over run, change in y over change in x. So my x's are the number of computer games. So this slope means it's $156 for 4 games, okay? All we did was we took our label for the y and applied it to our change in y. We took our label for the x and applied it to our change in x. Now this can actually be simplified. 4 goes nicely into 156. If you didn't know, you could divide it out. 4 goes into 15 3 times. It's 12. There's 3 left over. 4 goes into 36 9 times. Okay? So what this means now is we've simplified it by dividing. This 39 is really over 1. And we can apply the same thing. 39 is our change in y, which is related to our y variable, our total cost, $39. Our 1 relates to our change in x, and our x, if we follow it up, is our total number of games. So here, our slope means $39 per game. Okay? And we should really write that as a full sentence to show that we understand its meaning. $39 per game. Let's do another one, okay? This table shows how a tiled surface area, okay, the area that tiles cover, changes with the number of floor tiles that you lay down, okay? So here's our floor tiles, that's our x, our independent variable, and then the area, which is dependent on that, our y, is here. So I'm going to pick 2. Every time I am picking 2 values. I'm going to choose my first. This time I'll choose the second one. It doesn't matter which one I choose, okay? Now from there, I'm going to do my change in y, my rise, okay? So I'm thinking y's over x's. I'm going to do 96 minus 48 over my change in x. If I start here for my x, I got to go up to that one. 6 minus 3. Again, I started with 96 for my y's, so I have to start with the 6 for my x's on the bottom. Well, 96 minus 48, I borrow 8, and I get 48. Over 6 minus 3 is 3. So again, if I want to explain what this means in context, explain its meaning, the 48 goes with my y's. My label for the y's is the area or the surface area. So 48, and what does this say right there? Is it, I can't read it. This is too pixelated. It says inches squared. So 48 inches squared. And the 3 goes with our x's, and our x variable is floor tiles. So what this means is that there's going to be 48 inches squared covered by 3 tiles. Okay, I did my change in y over my change in x. Once I got that ratio or that fraction, I look, my y is inches squared, it's surface area, and my 3 is tiles, so I'm going to label it tiles and write out the sentence. Again, you should check and see if this can be simplified. And this one, again, can be simplified, okay? It simplifies to a whole number. 3 goes into 40 once, or 3 goes into 4 once. There's 1 left over. 3 goes into 18 6. So this is really like 16 or 16 over 1. Again, 16 goes with the y values. Our y is surface area in inches. Our 1 goes with x's, which is floor tiles. So it's 1 tile. So our sentence here would be 16 inches squared are covered by 1 tile. Change in y is found by subtracting. Change in x is found by subtracting. We put labels with them and we can write it as a sentence. Okay? That's how we find our slope, okay, or our rate of change from a table. Pick 2 points, subtract your y's as a numerator, subtract your x's as a denominator. Next, we're going to look at finding rate of change or slope from a graph. Now, this is really similar to what we just did with a table, except all those coordinate pairs are actually graphed. So we're still going to pick 2. Here they're going to tell us which ones to pick. And we're going to do our change in y over our change in x, our rise over our run. Okay, so let's look at the problem. This graph shows the number of people who visited U.S. theme parks in recent years. Find the rate of change for this to this and for this to this. So this is 2 different rates of change. One is from 2000 to 2002, and one of them is from this date range, 2002 to 2004. So let's start by doing 2000 to 2002. Okay, this is just my label. I'm going to do my rate of change, meaning I need to do my change in y. If I look at these are not coordinate pairs yet. I need to make them coordinate pairs. Okay, so this first one is going to be over to 2000. I want you to write in these coordinate pairs, comma 317. My second point here is over to 2002, comma, my y value is 324. My next point, I went over 2004, comma, up 325. And then our last coordinate pair, we went over to 2006 and up to 335. Okay, and close that parentheses. So each of these now we have an x, comma, y, an x, comma, y, all of them, an x and y value. So to start off, we're thinking rate of change is like slope. Slope is rise over run. So rise, change in y. I'm going to find my 2 points, one for 2000, one for 2002, and do my change in y. Okay? For 2000, my point is 2,317. And for 2002, my point is 2002, 324. Okay? I'm going to do my change in y, which means I subtract my y's. I'm going to do 324 minus 317. Now, if I start, my change in y with this y, I have to do my change in x starting with this. So I'm going to do 2002 minus 2000. Okay? I'm going to subtract these out. If I think about it, I can kind of do this with mental math. It's just going to be 7. Over 2002 minus 2000 is 2. And this means something. I could simplify that to 3.5, right? But if it's a fraction and it can't be simplified to a nice whole number, I might as well just keep it as a fraction. Remember, slope makes sense if we're graphing it to be a fraction, rise and run, okay? To explain this, I'm going to look at this 7, and this 7 means something. These are my y values. Instead of looking at what the y is on the table, I'm going to look at what my y label is on my axis. And if you look at it, it says the attendance in millions of people, okay? So this is 7 million people, okay? And here we have 2002 to 2000. These are years, so this is in 2 years, okay? Now, when we look at this slope, because we're talking about people and years, we want to say whether the attendance to this amusement park is increasing or decreasing. And looking at this slope, okay, reading it left to right like a book, it is increasing. So our sentence here would be that our attendance is increasing by 7 million people every 2 years. Okay, so we wrote a sentence about what it means based on our change in y, which is 7, and our change in x, which was 2. The y stood for millions of people. We found that from our y-axis. And the 2 is our years, which we found from our label on the x-axis, our change in x. Okay? I want you to pause the video. Okay, I'm going to erase this one, and I want you to try to do 2002 to 2004 on your own. Okay? You might have a little space. Maybe you want to do it in the margin here. I'm going to erase this myself. I want you to try it, and then we'll go over it together. Okay? All right, let's look at our rate of change now. Hopefully you gave it a go for 2002 to 2004. So I'm thinking in my head, rise over run, change in y over change in x. So I need to know my y's, and I need to know my x's. I'm going to look at 2002, which is right here. I already used that point once. 2002, comma, 324. I'm going to look at my other coordinate pair for 2004. So I'm going to come over here. It's 2004, 325. Okay. I'm going to do my change in y. So I look at my two y's and I'm going to subtract them, starting with this one. So I'm going to do 325 minus 324. I'm going to do my change in x's. If I started with this y, I have to start with that x. So 2004 minus 2002. Here, if I subtract those, I get 1 over 2. Now, again, I could simplify that to 0.5, but there's no reason to. Slope or rate of change makes sense to be as a fraction, okay? And I'm going to put 1 goes with my y's, which is attendance in millions. So this is 1 million people. And this 2 goes with my x, and our x label again is years. So my sentence here, I look at it, even though it's almost flat looking, it still is positive, okay? Here, the attendance increased, because it went up, our slope is positive, by 1 million people over 2 years. Okay? 1 million people, because that was our label on the y, over 2 years, our label on the x. Change in y over change in x. Although our last rate of change is different from this one, if we look at our graph, this section is linear, but this section has a different slope, okay? Our slope before was a little different than 1/2, right? It was actually top heavy. It was improper versus this one, which is not, okay? This graph is actually not entirely linear. We can't put a ruler on it and have every dot fall in a row. But each section is linear, which is why we came up with a couple different slopes for what looks like the same graph, okay? Keep in mind that your rate of change is constant for a function, okay? If it's always the same between any pair, then you have a slope, okay? It's a constant rate of change. However, here, because we had little line segments, each segment is going to have its own slope, its own steepness, because they're not all the same, okay? But if we're doing a linear equation, then all of them should fall perfectly in a row. Let's take a look at our last thing, which is identifying the slope from 2 points, okay? All right, this is the last thing we're going to look at as far as calculating slope, and it's calculating slope from a pair of points, okay? We can assume that both of these points are going to be on the same line, which means we can find the rate of change, or the slope, in between them, okay? Now, initially, you see them. I put little graphs. You're like, score, I'm going to graph points. Well, you can. In fact, I encourage you to graph points to check your slope. When they're close like this, that's fine. But what if one of your coordinate pairs had like a 52 in it? You don't want to graph that over 3 up 52. That's going to take a long time, and you're probably not going to have graph paper big enough. So instead, we need a different strategy, okay? We're still going to do our change in y over our change in x. That's what I should be thinking. Change in y over my change in x. My rise over the run, okay? But this time, when we plug in our numbers, we're actually going to develop what we call the slope formula, okay? One little formula that uses all letters that when we plug in our numbers in just the right order, we will always, always, always be able to calculate our slope. So, looking at this, that's what I want you to do. Normally, we do our change in y. So we would look at our y's, and we're going to subtract them. What we're going to call these in this aspects where we have just 2 points, okay, no table, no graph, we're going to call this, since it's our first point, our point 1, we're going to label this x1 and y1. That means this is the x from my first point and the y from my first point. Over here, this is like our second point. So we're going to call this x2 and y2. Now to find our change in y, we've been doing this minus that. And that's exactly what we're going to do, okay? We're going to take our y2 and we're going to subtract from it our y1. y2 minus y1, which in this instance is going to be 5 minus 0. Now our denominator, our x, is our change in x, our run. So we're going to do, normally, since we started with our 5, we would do 1 minus negative 2, which is x2 minus x1. 1 minus negative 2. So you can see how we come up with this equation from these points. Now we're just going to solve them like we did before, okay? 5 minus 0 is 5 over, and this is where, again, there's been several times this year that if you haven't been good with positives and negatives, it's going to nip you in the butt, okay? You got to take care of it. So here, I have two negatives next to each other, which means they cancel out and become a plus. So I really have 1 plus 2, which is 3. My slope is 5 over 3. Now I'm going to prove that my slope is 5 over 3. Watch. Okay, I'm going to graph negative 2, 0. Negative 2 up 0. Now I'm going to graph over 1 up 5. Over 1 up 1, 2, 3, 4, 5. And I'm going to connect them. Now, again, I want to prove that 5/3 is my slope. I'm going to count my boxes. 1, 2, 3, 4, 5. My rise was 5. And now I'm going to count my run. 1, 2, 3. My run is 3. Okay? So I know my 5/3 is right, and I know it's positive because reading it left to right, it looks like it's going up. So from this point forward, the big thing you want to remember, okay, is your slope formula. y2 minus y1 over x2 minus x1. What I'd like you to do is try the 4 other graphs that are listed on the bottom of this sheet. Each of the slopes is going to be different. You're going to have a positive one, a negative one. You might have one that looks even funkier, okay? If you're curious about what those possible zeros might mean, then I'd suggest you look back at your flip book, the y equals mx plus b1, and look underneath slope to figure out what type of slope it is. I'll tell you, I think one of these examples has an undefined one. And if that doesn't mean anything to you, you want to look back at your notes. Okay? We will go over this next class. We'll practice finding slope over and over and over again, but now you have some notes to be looking at for reference. Okay? Make sure you do these 4 problems, and I will see you in class. Thanks!